All right, so we're going to move on to a different type of receptors. These are our chemoreceptors. And the two that we're going to look at are taste and smell. So gustation is also called the sense of taste. The stimulant are the tastants that will react with our taste buds on our tongue as well as inside the cheeks and roof of the mouth. So some of the bumps on our tongue are what's called lingual papillae, help to sense the food texture. So that's also one of the sensations of dealing with your food, knowing the texture of your food as well. So in order to actually have taste, we have what's called taste cells, and in there we have our apical microvilli. These are taste hairs. Those are going to be the receptors for our taste molecules. So when we chew up stuff and we basically dissolve it into our saliva, let's be nice and gross. Hey, it's the real world thing. The receptors are actually going to be on those epithelial cells. That's actually your receptor, and then the signal is then sent to a neuron to then go to your brain. We do have some basal cells that help to replace them, so about every 7 to 10 days. So that's why if you've ever burned your tongue on a hot coffee or something, and it takes a few days to get new taste cells, that's because these are taking the time to replace the ones you burned off. So this is a taste bud. So we have our little bumps on the tongue. So that's what this is. And then go inside that. So this little tiny square, barely see it, is this section blown up. So these are our taste hairs. So whatever we've eaten, that saliva that has our food particles and it dissolves and has to get in that little tiny crack and then finally get in this tiny little hole to actually activate our taste. So you might want to slow down when you're eating, making sure you chew well enough so you can actually taste the food you're eating. Okay, so in order to taste stuff, it has to be dissolved in the saliva and get into that actual taste port. Now with our with our taste sensation, we have 5 of them. Salty, sweet, umami, which is a Japanese word for a meaty taste, sour, or bitter. The spicy flavor, so like a hot pepper or flaming hot Cheetos, that's actually not a taste. It's actually the capsaicin or other chemicals in the spicy element, such as the chili powder or whatever, that actually stimulates your pain receptors, so our nociceptors, instead of stimulating the taste buds. So spicy isn't actually a flavor, no matter how enjoyable it is. So what you're actually tasting, so to speak, might be the other stuff maybe garlic powder, or onion powder, and the Flamin' Hots, whatever the flavoring is. I've never looked at it because I don't care. I'm just going to eat it. Okay, so where are we going? So we have 3 different neurons where the taste information is going to go and then get to the brain. So that's our facial nerve, glossopharyngeal nerve, and vagus nerve. Getting information from different areas of your mouth and the back of the throat. So we're going to send this information to 2 different areas. So the first one is the hypothalamus and amygdala. So that is helping to control our autonomic reflexes, such as salivation, as in, oh, I taste something I like. I want to taste more of it. So more saliva, more able to dissolve the food, and so therefore more getting into our taste pores. It also controls gagging and vomiting. So some people with certain textures or certain flavors, for whatever reason, it triggers for them to gag up or possibly even vomit up the food. Or also dealing with, for example, some of your chemicals, like a household cleaner, or, for example, there's a battery company that is putting a bad taste on the outside of the little small batteries to make sure that kids don't swallow it. So if they put it in their mouth, they're going to automatically spit it back out because it doesn't taste good. So that's part of our determining the taste of stuff. The other location is to the thalamus. The thalamus is going to send the information to our postcentral gyrus, so we actually can have a conscious sense of taste. So actually get the sensation of that we're tasting stuff. Some of this is information from the thalamus is also sent to our orbitofrontal cortex so that we can take the information of what we're smelling as well as what we're seeing so that we can create a whole memory as well as looking at the food. So it's like sometimes if you have something that you really love, but it looks just like horrible, and it's like, this does not look nice looking at all, but it tastes really good. And so you ignore the fact of what it looks like, even though you might have to take a second to, to overcome that whole, this don't look good, but you know it's going to taste good. So you still eat it anyway. Same thing, if you do see something you don't know what it is and it doesn't look good, hopefully it also smells good at least. So you can like, okay, maybe I want to eat this. So taking in that information of, should I eat this? And this also helped us while, just really long time ago, ancient time, prehistory, is this a good berry? Nope, it stinks. I probably shouldn't eat it because most likely it was poisonous. Okay. Let's move on to smell. So same thing, we are detecting little tiny particles, so our odorants, which are chemicals, of what we're breathing in. So if we smell poop, there's poop all up in your nose. So little tiny particles of poop. So with our olfactory cells, these are the specific neurons for our sense of smell. They're the only ones that are exposed to the outside environment. We, as humans, can detect 2,000 to 4,000 odors. And I think in dogs, it's at least 10 times as much. So our odorants are little particles of whatever we're smelling that gets detected by these little nerve endings here in our nasal chamber. The information goes up to our olfactory bulb, the section here, going through the holes in that cribriform plate, like we talked about for the bone exam. And then this olfactory tract, which eventually becomes your olfactory nerve, is going to go toward your brain so you can tell your brain what you're actually smelling. So this is a more detailed view of what I just said. So our little particles or whatever we breathe in, that gets detected by these little nerve ending, these olfactory hairs, and then the information is sent up through those holes in the cribriform plate to our olfactory bulb. So each of these little areas, that's how we're able to detect different senses. So we have different areas that are going to be stimulated for our different sense of smell, so our different smells that we can detect. And then eventually all of that's sent to the brain. There is a layer of mucus that does help to coat and protect, as well as get the stuff that you want to smell to stick it to those olfactory hairs so you actually can detect it, but kind of has a dual job there. So like I just said, the olfactory neurons are the only ones exposed to the outside environment, so they have a short lifespan because they are exposed. But we still, just like with our taste cells, have basal cells that are going to become our new olfactory cells. So this one is going on how it actually works. So we have a second messenger signal for getting the actual change in our receptor potential. You don't have to actually know this. So instead of being a receptor for poop or McDonald's fries or whatever, there is a second messenger signal to actually get the start of our action potentials. So with our olfactory receptors, again, they adapt quickly. So again, grandma's mothballs, eventually that smell is going to at least not be sent to the brain. So it's going to get blocked out. As in, okay, we don't need to know that grandma's house still smells like mothballs. Some odorants can act on our nociceptors, so the ones for pain, such as ammonia, which is a house cold cleaner. Menthol, which if it's strong enough, it can affect the pain ones, even though it smells nice. Chlorine, so again, another cleaner one. If you've ever been to a pool that's inside and all that chlorine from the pool. And part of the reason why you smell it is because people keep peeing in the pool. But that smell is what is you're smelling and possibly can act on those pain receptors. And then, like I said earlier, the capsaicin of your hot peppers, so that's spicy. You are triggering your pain receptors, not a actual taste or smell receptor. Okay, so just going through the pathway. So once olfactory cells detect it, it goes to our olfactory bulb. Again, each glomerulus, each little ball detects a particular odor. And then all that information goes on our olfactory tract, and we're going to different locations. So we got our olfactory cortex, our actual primary sensory section of the brain for just receiving the information, and then we're going to send it to, for example, association cortex, so you can figure out what the heck it is. And it's also sent to other areas. So one place it's sent to is the hippocampus. This is why your sense of smell is your strongest sense that is tied to memory, because that information is going to the place where you're prepping your short-term memory to be stored as long-term memory. It also sends to your amygdala, so this is why sometimes you smell something and you actually can have a happy response to, "Ooh, I really like that candle," or as in, "Oh my God, why would someone burn that in their house?" So you're still getting a emotional response from the amygdala from what you're smelling. Also being sent to the hypothalamus, so part of our just coordination with other areas of the body, having some visual reactions to stuff. Same thing with our insular cortex, that is just helping us make sense of what we're smelling. And then the orbitofrontal cortex, like we talked about earlier, with our taste. So let's say like for example, let's say I have a piece of food and it looks like a certain type of food, but then I eat the food and it tastes completely different. That's going to throw your brain all kinds of off. Why? Because it ties what something should taste like to your smell of it as well as the look of it. So when something's off, your brain gets a little confused. Where are we? 12 minutes. I'm going to stop here, even though we're only at 12 minutes, just because the next section is so long that we'll see what happens. I might put hearing on one and vision on the other, or see if I cram it into all one, which may probably not happen. That might seem too long because I still got 30 slides literally. So we'll see what happens.